to the second segment of the fourth lecture for the online series of lectures for the course of Dynamical Systems. So in the first segment, towards the end, we were discussing an example, and we have seen there that for any point P Q in R2, the omega limit point for the orbit of this point PQ in R2 is the zero vector. For lambda strictly less than 0. Okay, this is what we have seen towards the end of first segment. Okay, so now let this point PQ be such that this is not the origin. That is, P and Q are not both 0, and we have the constraint lambda to be strictly negative. Then our claim is that the alpha limit set for the orbit of such a point PQ is empty. This is equation number 5. So equation number 5 is our claim. Let us try to prove this claim. 5. Note that if Q is not equal to 0, so we are going to have this vector PQ to be not equal to the vector 0, 0. And one of the ways this can be done is Q is not equal to 0. So if this is the case, then the norm of the flow vector theta TPQ, the square of this norm, is going to be equal to e to the 2 lambda t times p square plus q square plus t square q square plus 2tpq that we have shown earlier. Okay, work done earlier. In the first segment, we have shown this. So now, let me rearrange this expression a bit to make it look like q square plus p square plus 2pt q plus t square q square, which in turn can be written down as q square plus p plus tq whole square. Okay. And this is going to be strictly greater than, no, it's not strictly greater than, it is going to be greater than or equal to q square e to the 2 lambda t, because this is going to be greater than or equal to 0. Okay. And by the way, the case Q is not equal to 0, we are considering this case, and this has two subcases, right? One, Q is not equal to 0, p is also not equal to 0, and the second subcase is q is not equal to 0 and p is equal to 0, right? Because we want this vector pq to be not equal to the 0 vector. So there are two subcases to be considered. Okay. So from what we have, we can immediately see that the norm of this vector theta t comma pq is greater than or equal to the absolute value of q times e to the power lambda t. And you see that lambda was taken to be negative, right, in this case as well. And this guy approaches infinity as t approaches negative infinity, since lambda is also negative. Consequently, one has the limit of the norm as m approaches infinity to be infinity for any sequence of real numbers Tm such that Tm approaches negative infinity as m approaches infinity. So what does one conclude from that? One arrives at the fact that this limiting expression does not exist for the case this limiting expression does not exist for the case q is not equal to 0 and lambda is strictly negative. This is what one concludes. Okay, so let me get rid of this part now to consider the case q is equal to 0 and p is not equal to 0. Okay. This is the other possibility one can have, right? Okay. While we always have, as earlier, lambda to be strictly negative, note here that the norm of this vector the square of the norm to be equal to e to the 2 lambda t p squared, since q is identically 0. Okay, and this implies that the norm itself is going to be equal to e to the lambda t times the absolute value of p, and this goes to infinity as t approaches negative infinity. Why? Because lambda is negative as well as earlier. Lambda is negative as earlier. Okay, So again we have the same result, right? Meaning that the limiting expression does not exist. Okay, good. Thus we have been able to prove that whenever we have this vector to be not equal to the zero vector and lambda is strictly negative, then the alpha limit set of the orbit of this point PQ is empty. Okay. Okay. Good. Finally, one notices that the norm of the vector theta t00. Okay, now PQ is the vector PQ is the zero vector. If this is the situation, then the norm of this vector is identically equal to 0. In other words, I can write this fact as theta t 00 approaches the vector 00, since whenever the norm of a vector is 0, that means that the vector itself is a zero vector. So this guy approaches the zero vector as t approaches negative infinity for any lambda to be non-zero. Be positive or negative, doesn't matter. Okay. And this implies that for any sequence of real numbers, Tm such that Tm approaches negative infinity as m approaches infinity, one must have this limiting expression to be the zero vector. So which means that the alpha limit set of the orbit of the vector zero vector is the zero vector itself. Only. Important thing to note in this context is that here is that 0, 0 is a fixed point of the underlying dynamical system. That is, theta t comma 0, 0 is going to be 0, 0 for any t in the set of real numbers, which we have stated here that 0, 0 is the fixed point of the underlying flow map. Okay, and hence 0, 0 is an equilibrium point according to the definition of equilibrium point that we discussed in the beginning of the first segment. Equilibrium point okay, so from what we have discussed so far, it is immediate that 0, 0 is the only omega limit point and alpha limit point of the orbit of the zero vector. In other words, they are both equal to the zero vector. Right? I have to put it inside square bracket. Okay. Just now, properties of limit sets. Okay, which involve certain definitions. So let me get started with the definition of invariant sets. Let theta from R cross U to U be a dynamical system on the U, an open subset of R to the n, a subset A of this open subset U is said to be invariant under the flow theta if for every q in A, theta t comma q is also in A for all t in the set of real numbers. Okay, so this is the definition of invariant set. I'll give you an example of invariant set, which is example 2 for this lecture. For a given point in the open set U, the orbit of P, denoted by gamma sub P, is invariant under the flow. Is invariant under the flow. To see how this happens, first note that from the definition of orbit, if Q is a point in the orbit of P, then Q is equal to theta T0 comma P for some T0 in the set of real numbers, right? This follows from the definition of an orbit. We then have that for any T in the set of real numbers, theta T comma Q is equal to theta T comma, so let us replace Q with theta T0 comma P, and then by using the property of flow map of the underlying dynamical system, we can rewrite it as this is equivalent to saying this is the same as theta T plus T0 comma P, and it is of course inside the orbit of P from the definition of orbit, right? Hence gamma sub P is invariant under the flow of theta. Under the flow theta. Okay, so we have seen that the orbit of a point P is an invariant set. In the following proposition, we will see that the limit sets of an orbit is also invariant. Okay, so let me state the proposition first and then I'll prove it. Proposition 1. Let theta from R cross U to U be a dynamical system on U, an open subset of R to the N, for any P in this open set U, the omega limit set and alpha limit set of the orbit of P are closed invariant subsets of U. Okay. All right. So here is the proof. We prove the result for omega limit set only. Okay. The arguments for alpha limit set are analogous. Okay, so we first try to prove that. We first show that the omega limit set of gamma sub P, meaning the orbit of P, is invariant. Let Q belong to this omega limit set of gamma sub P. Then, using the definition of omega limit set there exists a sequence of real numbers Tm such that Tm goes to infinity as m approaches infinity, and the following holds. Let me erase the statement here. And Q is equal to this limiting expression as m approaches infinity. This is equation number 6. We number it as equation 6. Okay, so since Q is an omega limit point of the orbit of P, we can write Q as this limiting expression. We have seen in lecture 3 that for each time in the set of real numbers, the dynamical system theta from R cross U to U induces a diffeomorphism. By diffeomorphism we mean a bidifferentiable map, meaning that a differentiable map with a continuous, a differentiable inverse induces a diffeomorphism on U, denoted by theta sub t from U to itself, and given by theta sub t at P is going to be simply theta t comma P, and this is going to happen for all P in the open set U. Since theta sub t is a diffeomorphism, it is of course continuous. It is definitely continuous. Using its continuity, one obtains from 6 that using theta t's continuity, using its continuity, one obtains from 6 theta t comma q is equal to theta t comma the limit of theta tm comma p as m approaches infinity, right? And as we have said earlier, using the continuity of this diffeomorphism theta t, one can take out the limit and write it as limit as m approaches infinity of theta t comma theta tm comma p. Okay, so this is equation number 7, and this is going to happen for any t in R. On the other hand, one observes that theta t comma theta tm comma p is nothing but using the is nothing but theta t plus tm comma p using the properties of flow map of a dynamical system, and this in turn is equal to theta tm comma theta t comma p. Okay, so this is going to be equation number 8. Good. And then by combining 7 with 8, one immediately finds the following. Combining 7 with 8, what was 7? 7 was this, let me write it for you here, it has been erased. Theta t comma q was theta, limit m tends to infinity, theta t comma theta tm comma p. This was 7. So combining 7 with 8, one obtains theta t comma q is going to be equal to limit m approaches infinity, theta tm comma theta t comma p. Which, using the definition of omega limit set, yields that theta t comma q belongs to the omega limit set of the orbit of theta t comma p. Okay, theta t comma p for any t in R. This is our equation number 9. Okay, let me erase this part now. But important thing to note here is that gamma sub theta t comma p is equal to gamma sub p, meaning that the orbit of theta t comma p is the same as the orbit of p for any t in the set of real numbers. Let us prove the result for a given t in R. Okay. Indeed, observe that if Q belongs to gamma sub theta t comma p for a given t in R, if this is the case, then of course from the definition of orbit, Q is equal to theta t prime theta t comma p for some t prime in the set of real numbers. Okay, and by using the property of the flow map of a dynamical system, we know that this is going to be equal to theta t prime plus t comma p, right? So hence we have seen that there exists t prime plus t belonging to the set of real numbers such that Q is equal to theta t prime plus t comma p, and therefore Q belongs to the orbit of P. Okay, so it then follows that we started with the fact that Q belongs to gamma sub theta t comma p, and we arrived at the fact that Q belongs to gamma sub p. It means that gamma sub theta t comma p is a subset of gamma sub p, right? For the reverse inclusion, observe that if we choose Q to be in gamma sub p or the orbit of P, then there exists T prime in R such that Q is equal to theta T prime comma P, right? Follows from the definition of an orbit, and we can rewrite this as theta T prime minus T plus T comma P, right? Which means that this is nothing but theta T prime minus T comma theta T comma P, using the property of a flow map of a dynamical system, right? Hence we see that there exists T prime minus T in the set of real numbers such that Q is equal to theta T prime minus T comma theta T comma P. Therefore Q belongs to the orbit of theta T comma P. So again we started with Q belonging to gamma sub P, and we ended up proving that Q belongs to gamma sub theta T comma P, proving that gamma sub P is a subset of gamma sub theta T comma P. So we have been able to show that therefore gamma sub P is equal to gamma sub theta T comma P. Okay, good. So recall that in equation number 9 we showed that theta T comma Q belongs to the omega limit set of the orbit of theta t comma p. This is what we proved in equation number 9. Now that we have shown that gamma sub p is equal to gamma sub theta t comma p, theta t comma q belongs to the omega limit set of the orbit of p, okay, for any t in the set of real numbers. Good. So let me summarize what we have shown. Therefore, we just showed that if q is in the omega limit set of the orbit of p, then theta t comma q is also in omega limit set of orbit of p for all t in the set of real numbers. In other words, omega limit set of the orbit of p is invariant under the flow you're considering. Okay, next we want to show that. Next, we'll show that the omega limit set of the orbit of p is closed in U. This is what we will show now. Okay. Good. So what we want to show here is that the omega limit set is closed in U. So it is equivalent to showing that the complement is open in U, right? We'll argue by contradiction, meaning that we'll assume the contrary. We'll argue by contradiction, we'll assume the contrary, meaning that the complement of the omega limit set is not open, and then we'll show that it leads to some contradictory fact, and then that will prove that this assumption is incorrect, meaning that this is open. This has to be open. Okay, so let me draw a picture for you first. So this is what we take to be the open set U that we start with for the dynamical system, and inside which there is this set, the omega limit set of the orbit of P, and the rest is the complement, right? And our assumption is that this sky is not open, right? That is, so using our knowledge of analysis, it tells us that there exists, since this is not open, there exists Q here in the complement, and a sequence of points Qn. here on the other side of this border, okay, in the omega limit set, such that this guy converges to this point. Okay, this is going to be the case since this is not open. Okay, limit of this is going to be 0. Okay, this is our equation number 10, and let me put a side note here. If omega if the complement were open, no such point would have existed. No such point, no such sequence would exist in the omega limit set. Okay, here no such sequence would exist if this were open. But this is assumed to be not open, and hence such a sequence exists. Okay. Now we use the fact that each of these points of the sequence belong to this set, omega limit set, and hence, so now since each qm is in omega gamma sub p, we can find a sequence of real numbers. The sequence is indexed by 2 natural numbers, okay, but we are only going to vary the later one, tmn, and we are going to vary n, okay, such that tm comma n goes to infinity as n approaches infinity, and the limit as n approaches infinity, theta tmn comma p is going to be equal to qm. This is a limit point. This belongs, for each m, qm belongs to this omega limit set, and hence this holds. Okay, good. Now I just erased equation number 10, which tells us that the sequence qm converges in norm to the point q of the complement of the omega limit set. Okay, and so using basic analysis, we immediately see that for positive epsilon, for all positive epsilon, there exists a natural number such that the norm of the difference of these two numbers can be made arbitrarily small, right? Whenever m is bigger than this natural number, n, big N. Okay, this is our equation number 11. Okay, now our duty is to construct a sequence of real numbers. Also construct a sequence of real numbers as follows: T m comma k sub k of m. Okay, so this is something that we are going to construct by picking a big enough k of m. Okay, by picking a k of m for each m in the set of natural numbers, such that the norm of theta t m comma n comma p minus qm is less than 1 over m, and this is going to happen for all m in the set of natural numbers, and this is going to take place whenever n is bigger than that chosen big number. Okay, this is how we are constructing this sequence. Okay, so good. Now, based on our construction, this implies that the norm of this difference, theta t m comma k sub k of m, which we have just constructed, comma p minus q is that point of the complement of the omega limit set, okay, is less than or equal to, by triangle inequality, it can be written down as the sum of two norms. One is theta t m comma k of m comma p minus qm, and the other contribution is the norm of q minus qm. Okay, and well, this is taken to be smaller than epsilon over 2, right? And this guy is taken to be smaller than 1 over m, right? So this whole thing is smaller than 1 over m plus epsilon over 2. And if we want this thing, the whole thing, to be smaller than epsilon, then we of course want 1 over m to be smaller, 1 over m to be smaller than epsilon over 2, right? And in other words, we want 2 over epsilon to be smaller than m, right? For this guy to be smaller than epsilon over 2, and this guy is already epsilon over 2, so the whole thing would be smaller than epsilon. And for this to be smaller than epsilon over 2, we want m to be greater than n. So we want m to be greater than 2 over epsilon. At the same time, we want m to be greater than n. Okay, so this can only happen if we choose m to be greater than the maximum of these two numbers, right? N and 2 over epsilon. So if we choose m big enough such that m is greater than the maximum of these two numbers, n and 2 over epsilon, we can always make it arbitrarily small. Okay. Now, let me summarize what we have constructed so far. Hence, we constructed a sequence of real numbers Tm, k of m, okay, such that Tm, k of m approaches infinity as m approaches infinity, and the limit of this expression as m approaches infinity is going to be equal to q. Okay. This is what we have seen, that it can be made arbitrarily small. The difference can be made. The difference of this and this can be made arbitrarily small as m approaches infinity. Okay. So hence, by definition of omega limit point, Q must be in the omega limit set of the orbit of P, right? Because this holds, such a sequence exists. And this thing is in direct contradiction of the assumption that Q is in the complement, right? Is in the complement of the omega limit set of the orbit of P. Therefore, our fundamental assumption was incorrect, and omega limit set of the orbit of P must be closed. QED. Okay. All right. So we'll end the second segment here, and in the last segment we will study a couple of examples in detail and study the corresponding limit sets there. Thank you for attending this second segment.